Hello everyone, my name is Benedek Horvat, and today I would like to introduce you the results of our collaboration with my fellow early stage researcher Alessandro Colantoni in the Locomote project. The title of our collaboration was Towards Continuous Consistency Checking of DevOps Artifacts. The motivation of the research was that there is a broad landscape of DevOps tools which help the work of software engineers to build, test, and continuously deploy new versions of their softwares to production or to test environments. These DevOps tools use different configuration scripts, textual artifacts, to set up these DevOps pipelines. These configuration files are usually semantically related, which means if you change something in one of the files, then you usually have to change something else in other configuration files. However, maintaining these consistencies is a lot of work and can be cumbersome and can lead to bugs that are difficult to discover. Therefore, our goal was to develop a solution for the continuous consistency checking of DevOps artifacts. As an example, we used Keptn. Keptn is an open source cloud native application lifecycle orchestration project which helps you to define continuous delivery pipelines with quality gate criteria. As an example, we use the service level indicator and the service level objective languages of Keptn. In the service level indicator, you can specify what runtime measures your system should fulfill in order to guarantee that it's operating well. In the service level objective, you can specify certain criteria under which these metrics are accepted, or if they exceed these criteria, then they are failing, which means you need to mitigate those problems at runtime. As you can see in the example, the service level indicator and the service level objectives are depending on each other. More specifically, in the service level objective, you have to specify a service level indicator for which you define the pass criteria. These two languages use different configuration files to specify these settings. Without any help, you have to manually adjust that the service level indicator name is the same as the one that you are using in the SLO file. Therefore, our goal was, in this running example, to ensure the consistency of the indicator names. Starting point of the solution is that we have a DevOps engineer who updates these aforementioned configuration files in the DevOps tools. After that, the DevOps tool is pushing the new versions into a Git repository. Git is notifying an adapter which sends these newly pushed configuration files to the consistency maintenance service that we proposed. And it is the first step of the continuous maintenance service. The configuration files are parsed to models for easier handling. After that, the parsed models are continuously updating the changes. As soon as we get the updates, we do an incremental consistency check to see what changed in the configuration files. And if we detect validation errors, then a model repair service is trying to automatically repair these inconsistencies. If the repair phase was successful, then the updated models are serialized back into their original textual form. They are sent back to the DevOps tool, and from the resolved errors, we are generating a report, and this report is sent to the DevOps engineer so that he can inspect that there were certain changes and can make sure that these changes were correct. The question that we faced was how to check the consistency of artifacts that belong to different languages. So for example, the SLI and the SLO language. To solve this problem of handling different JSON-based configuration files, because in the previous examples, SLI and SLO were JSON artifacts, we used a JSON-EMF bridge, the JSON Schema DSL developed by Alessandro Colantoni and presented on the Models conference in 2021. The interested readers can look up this paper in which Alessandro and his co-authors propose a solution to parse JSON files into EMF models, to make some changes there, and then to serialize the changes back to the original JSON representation, so that these files can be used both as textual artifacts and as models. By using this JSON-EMF bridge, we could introduce several benefits of the model-driven engineering to these DevOps tools. So more specifically, we can do several checks on the model, so to analyze, for example, their consistencies, or by implementing some validation rules, we can also check that these models are correct. And if the models are incorrect, then we can repair them automatically by implementing some model repair rules. And all these solutions rely on the fact that we have some models. These models are conforming to certain meta models. The meta models are describing the different concepts and the relationships that can be used in the models. If we have several models which conform to different meta models, then we can define a so-called linking meta model to connect these meta models and to enable the model validation on them, so to run model queries and model transformations on these connected models. Model queries are used to check the consistency of the models, and model transformations are used to fix the inconsistencies in the models automatically. To implement the model validation rules and the model repair actions, we use the Viatra model query transformation and validation framework. The validation rules are defined as graph patterns, as we can see in this example, and the model repairs are reactive model transformations. If we have a look at this example, then it defines a model query which checks that the objective's SLI field must refer to an indicator with the same key, so that we refer to an SLI in the service level objective model, then the names must be correct according to the SLI model. We return an error stating that this objective has an incorrect SLI referred. In the case study, as you could see in the beginning, we have the SLI meta model that is representing all the concepts that can appear in the service level indicator file. We have the SLO meta model, which represents all concepts and relationships that may appear in the service level objective configuration file. We have a linking meta model to be able to navigate from an SLI to an SLO model. And in this example, as you can see, we are checking that this response time P95 is the same as in the objective, this response time P95. In the next phase, we will see a demo. In this demo, we are changing the name of the service level objective from 95 to 94. This will trigger a problem because previously this was 95 and this was also 95, but now we changed it to 94. So our solution asks if you would like to update the SLO as well. So to referred name should be also 95, and when the user clicks yes, then these two values are synchronized with each other so that there will be no more errors in the model. In this case study, this was a very simple starting point. The two DevOps artifacts that we synchronized were the SLI and the SLO. Keptn has other languages as well that can be also used for synchronization. The limitations of our case study was that we created this linking model between the artifacts by hand, and this consistency management and maintenance workflow was just partially implemented. So we implemented the phases in yellow, but we didn't have time to implement the report generation. This is left as future work, and also the scalability evaluation is left as future work. To conclude our work, we proposed a so-called GitOps workflow to check the artifact's consistency. In the GitOps workflow, the Git is the central repository, and this is the single source of truth that triggers the validation workflow. The proof of concept implementation of the workflow was done, and several MDE use cases for DevOps configuration artifacts were introduced. For modeling, we made several contributions, but we have some future work left. For example, the GitOps adapter to reflect the Git structure as a mega model, and we could use query-driven soft links to maintain the linking model instead of creating it by hand. And for research-oriented purposes, we proposed an idea to implement incremental parsing. And then this collaboration was published on the DevOps workshop of models in 2021. Interested readers can look up the paper to learn more about the details of the workflow. Finally, we would like to thank our sponsors, the different grants who enabled us to do this work. And there are some references that we used in the talk. And finally, we would like to thank you your attention. And if you are interested, then please visit the Locomode website to learn more about the Locomode project. Look up the paper that we just presented, or you can also visit the implementation on GitHub.